Yeah, so moving on. So a lot of what I'll talk about next is based on work which we published at EACL with Isabel Papademetriou, Ethan Shi, and Richard on deep subjecthood. So yeah, parts of this will be new and parts of this will have been published here. So feel free to take a look at that paper. So in this next part, we're thinking basically about training subject-object classifiers and in a kind of probing tradition, right? So probing is become a kind of frequently used way of trying to recover something about what a language model has learned, right? So basically training some small classifier to then do a task. There have been also a bunch of issues pointed out with probing, specifically that they over-memorize, and maybe lead you to the conclusion that contextual embedding models aren't really capturing as that basically even if a probe recovers some task, for instance, Hewitt and Manning showed that probes can recover syntactic distance. It's been pointed out by Titov and Hewitt Lang and Pimentel et al. That probes might actually be over-memorizing, and that actually kind of in the way that we saw in the human experiments and the computational experiments, type level word embeddings might actually capture a lot of what's shown to be syntactic based on these kind of probing methods, right? So I like this from the Pimentel et al. Probing paper that when put into perspective, multilingual BERT representations do not seem to encode much about syntax. Much more information about syntax than a simple baseline. On part of speech labeling, BERT only improves upon fast text in 5 of the 11 analyzed languages by small amounts. But I think it's kind of interesting to ask this question, well, like, what are, is it maybe the case that those small amounts that are missed by type embeddings might be these kind of interesting cases, right? So maybe, if 90% of the time you get people add pets or people accept ideas and lie in a game, that's kind of, certainly the kind of thing we're getting with the type level embeddings. But maybe it's the case that these kind of more counterintuitive examples, or at least counterintuitive based on the lexical semantics alone, are something you might pick up with contextual models. So that's a kind of question we can ask, which is, what about these cases when contextual embeddings do help? Or put another way, just as we think that BERT and models of that type are capturing something about semantic, can capture semantic word senses based on contextual information, are they capturing something also about syntactic information? Right. So the tool we're going to use to get at this here is this agent subject-object classifier. We're going to later get into questions of ergativity, and so I'm going to be introducing the ASO notation, which sometimes gets used, where A is the transitive subject, O is the transitive object, and S is the intransitive subject. So to kind of foreshadow that, I'm going to be using A versus O here. And this is basically going to be the tool we use in this second and third part of the talk, is this A versus O classifier, kind of like the one we talked about for the subject verb object embeddings in the first part, but instead it's just going to be classifying. You don't get to see S, V, and O all at once. You're just going to see one or the other. So, right, in this part we get here for 24 languages, extract the sentences and grammatical rules from universal dependencies, feed them into multilingual BERT, and extract the contextual noun embeddings. And then we train a small classifier to predict if a given noun is an A or an O. And we're going to balance the training set to have equal numbers of A's and O's in it. Right, so a caveat here, and something we'll come back to later, is that we're working with the UD framework, right? So this is the universal dependencies framework based on what they call subjects and objects. And so it's inherently limited by their labels, the core oblique distinction, and various other things. And so, yeah, we'll kind of get into at the end questions of what are we actually classifying when we're classifying a subject versus an object. Right, but again, here we embed into BERT space get at each layer, at each hidden layer, we can extract an embedding for each token, and then train a small classifier to predict for something like the dog chased the cat, given the embedding of a novel token, which did not appear in the training set. Is it the case that the classifier will correctly say that mouse from the contextual, taken contextually from the L, watch the mouse, is an O, or we'll get it wrong and say it was an A. Right. So we can then, the same way we did before, take this classifier and say, okay, that's going to give us for each token, and we for multi-token words, we tried both ways of either taking just the first token or averaging across them. It didn't seem to make much of a difference. So the results I'll present here will be the average across tokens, which seems to be the kind of developing standard for this kind of thing. So it basically gives us a probability that a particular token is an agent, an A, as opposed to an O, an object. Right, and for each layer, we train a separate little classifier. So I'm going to show some results here, in this case for French, where the y-axis is going to be the probability that the particular token is classified as an A according to the model. The x-axis is the layer, so from 0 to 12 for all the layers BERT. And then there's going to be a line for things which are actually A's and things which are actually O's, right? So for things which are actually A's, at the kind of 0 layer, it's getting about 75% right, and then that goes up to actually like up around 95% as you get to higher layers. This one peaks actually slightly earlier, but usually they peak around layer 10. And then for O's, we see the opposite, where O's are correctly classified about 75, a little more than 75% of the time at layer 0. And then as you go through the layers, it gets more accurate. And we do this for 24 languages. And by and large, we get pretty good classification performance, right? And interestingly, at layer 0, that performance is consistently less good, right? So in all of these cases, the A and the O line start off closer together and then kind of get farther apart as you get up to higher layers, typically peaking around layer 10. So this is kind of an interesting question of, well, what's going on at layer 0? Right, layer 0 in a BERT model consists of kind of a combination of a word embedding piece and a position embedding. So the way that in BERT, you create layer 0, and that then gets propagated through and to create all of the rest of the layers, right, is by having, addressed by Latin is so flat. Yeah, that's an interesting question. Yeah, there are kind of, it's worth pointing out, there are some interesting cases that we'll get to. Actually, yeah, we'll get to kind of some interesting cross-linguistic variation. But yeah, it's an interesting point that Latin kind of starts off high and stays high. Maybe that we didn't see huge case effects here either, but Latin is a language where you would expect there to be quite a lot of information in the morphology. And so maybe, yeah, I don't want to tell it just so straight, but you would kind of expect that at lower levels, because there's a lot already in the morphology, that maybe Latin would do well. So we then use this technique here of, we can say, okay, we can break up layer 0 by kind of subtracting out the position embedding piece. So the position embedding, right, is basically just telling you where in the sentence the particular token appears, which is how kind of how word order information makes its way into the model. And then there's a piece without that, which will be the same at layer 0 for each token. And so what we do is we subtract out the position piece to get a kind of separate representation of a word, a kind of quasi-word embedding piece, which is the same for each token, regardless of context, and then the position piece. And so if we look at that word embedding piece, and then it takes a second to kind of explain what's going on with this plot. This is breaking up the kind of thing that we saw in the previous plot, but breaking it up by based on whether this word embedding piece, which is the same for a given token, regardless of context, thinks that the particular token is more likely to be an A or an O, and then split by that, and then what its actual role is, right? And so you can kind of think of this as, what does the word type predict for a particular word, whether it's an A or an O? And then how does that actually manifest itself as an actual A or an O? So this top left quadrant are things, up here, right? This top left quadrant here are things in which the word type itself gets classified as plausibly an A, plausibly an agent, and then it actually is an agent. And so for those, the kind of probability of being an agent starts out pretty high, even at word embedding piece in layer 0, and it stays high. And that happens kind of across languages. Down here, these are ones which are split to be the case, these are ones where if you were to look just at the type, at the word type itself, you'd be more likely to think it's an object, right? So these are the kind of email mentioned Judy examples, where based on just the word type, you think it's going to be an object. And so the word embedding level classifies it as very unlikely to be an A, but it ultimately does get it right, right? So as you go up the layers, the performance becomes pretty high. So around layer 9 and 10, it's really pretty accurate, although you have quite a bit more variability by language, and we'll get to that variability in the third section here. And you see a kind of similar pattern for O's, where things which are plausibly objects based on the word embeddings, and that actually are objects kind of stay relatively constant, whereas things which seem like they're probably A's, right? You would guess it's a subject just based on the type level information. As you go through the layers, get less likely to be classified as an O. Right, so the type level predicts A, but they're actually O's. By layer 10, you're starting to make more accurate predictions. And again, you have quite a bit of variability by language in ways we'll discuss. So here I'll just show a kind of cherry-picked, but I think interesting example of kind of ongoing work here, which is to take sentences that were in Gibson et al. 2017's noisy channel experiment, like the electrician stole the hammer, kind of sentences with plausible subjects and objects, and basically reverse them to make these implausible sentences, and then try to classify them. And depending on the sentence, they don't all look this clean, just to be clear. And this is kind of ongoing work, so I'm not going to present results in aggregate. You see these kind of patterns where if you look at the word embedding and the kind of contextual information over time for the electrician stole the hammer and try to classify the word electrician, right? The model thinks it's an A at the word embedding and at the 0 level, and that stays kind of constant. It gets a little better. But then for the hammer stole the electrician, right? If you just classify electrician out of context, you think it's a subject. But in context, the model learns over time to classify it as an object. But so by layer 7, you have like pretty strong classifications of that. So yeah, kind of a potentially tantalizing evidence, right? The contextual embedding seems to encode something about subjecthood, right? So if you train this little classifier, it seems like it at least enables you in classification space to make the prediction that something which, based on its type and its static embedding alone, becomes able to classify kind of correctly based on subject or object position. And it seems like it's probably doing that using some kind of position level information, right? So remember that word embedding, we were subtracting out the position information. So it seems like the position information, which basically is a way of getting word order information there, right? And subjects in almost all these languages come before objects. It seems like that's part of what's going on there. And it's kind of an open question how exactly it's doing that and one we're continuing to think about. So we could then ask, well, what is this classification actually doing, right? So this was kind of, in part, I think what Adina's question was getting at, which is, well, we're classifying subjects and objects based on UD labels, right? But there's all kinds of things that affect what's a subject, right? So there's agency and topicality and discourse status. So what are we actually doing when we're doing this classification? Is it just picking up on something about semantical? Sorry, somebody. Right? Is it just picking up on something about semantic role? Is it grammatical role? And what happens when those come apart? And how does that work across languages? And what can we learn by classifying intransitive subjects across languages that have typological variation about how that's handled? So that'll be the subject of the third part of the talk, and I will end part 2